Yes, class. So in the last class, yesterday we had completed till this point only, no? So what all did, am I audible to all of you?
Yes, ma'am.
Okay. So we had seen the differences between, Anushka, where were you? Last weekend also you were not present. Yesterday also you didn't come.
Ma'am, last week I couldn't join because of mock 1 had started. So just on Friday it got over.
Okay, okay.
Ma'am, in yesterday's class I was joining, but it was keep on showing that wait for the host to start the meeting.
At what time did you join?
Ma'am,
The class was at usual timing.
Ma'am, for the usual timing, I didn't get the link. I got the link for the 9:30 class.
But I had written it on the group that was sent by mistake, the timing. The main class was at the usual timing. I had written it
For
on
the
the
5
group
o'clock
also.
class, I didn't get the link.
Didn't you see the group? In the group, I have written it. Yes, others, I hope you all got the message on WhatsApp.
Ma'am, the message I got, but the link for the class I didn't get.
The link remains the same, no? Every Saturday and Sunday, you have the same link. With this link only, you join. There's the same link that you join with. So that link was of 6:30 only. Just the timing was different written. It was 10:30, IST 10:30 written. So that's why I had written it on the group that the class is at the usual timing. All right. So just do one thing, take the video lecture, just see it because a major portion was covered yesterday.
Yes,
Let us complete with this. So at any point you want to find out the separation of the central bright fringe from any of the fringes, whether it be dark or light, we have this one expression that is this expression we calculated x is equal to yn small d by capital D, where yn is equal to the separation from the central bright fringe to any of the fringes. X is the path difference, capital D is the separation between the slit and the screen, and small d is the separation between both the slits. Now see, if you have it specifically for bright fringe, so see for bright fringe, we already know the path difference is n lambda, where n is 0, 1, 2, 3, any number. So yn, which was x capital D by small d, instead of x, you can put n lambda. So yn will be what? N lambda capital D by small d. Now, depending upon whatever number of fringe you have, let's say first bright fringe you have, so you will put n as 1. So that will be 1 lambda d by d or lambda d by d. For second bright fringe, it will be 2 lambda d by d. Third bright fringe. This is just for bright fringe because we have already discussed the path difference is different for bright fringes and dark fringes. Or let's say, for example, you have eighth bright fringe you want to calculate. Separation of the central maxima from the eighth bright fringe. So that will be 8 lambda d by d. Whatever is the number of fringe multiplied by lambda d by d, you will get the separation from the central bright fringe. Suppose, let's say you have dark fringe. So instead of n lambda, you will put 2n plus 1 lambda by 2. 2n 1 minus lambda by 2. So when you put 2n minus 1 lambda by 2, you will get all the odd values. When you put 1, you will get 1 lambda by 2d. When you put 2, you will get 3 lambda by 2d. When you put 3, you will get 5 lambda by 2d. Let's say, for example, n's value is, let's say, 6. So 2n, instead of n, put value 6. Instead of 6, n put the value 6 minus 1. So this is 2n minus 1, where n is 6, lambda capital D by 2d. So this becomes 12, 11. So this is 11 lambda capital D by 2 small d. Like this. So any of the values you get, put it as it is, whatever value you have. So this formula is separate for dark fringes. For bright fringes, you have different formula. All right. Just do one thing, note this part down, then width of the fringe we'll see. Bright fringe and dark fringe.
Ma'am?
Yes, Anushka.
Ma'am, from this chapter, wave optics, how many topics are covered?
From this High-Ends principle we had done, and then interference we had started yesterday. So we are on completion of interference, and the last topic that is left is diffraction. So first we'll complete with interference, then we'll start with diffraction. It's a short topic, diffraction.
Yes, ma'am.
See class, next topic from this is width of the fringes. So width, it can be for bright fringes also, it can be for dark fringes also, fringe width, which you say. So fringe width does not mean the thickness of a fringe. Fringe width means separation between any two consecutive fringes. Suppose, let's say this is the bright one, this is also bright one, in between you have these dark fringes. So separation between these two dark fringes or these two bright fringes, this is known as fringe width. So how will you calculate it? See, the derivation part for this one is very easy to find out the formula. Separation between two consecutive dark or bright fringes. So bright fringes or dark fringes, even if you do the derivation part from both of the fringes, you can. So let's take the example of dark fringe. You can take for bright fringe, you will get the same answer. Dark I'm taking because dark becomes a little difficult to solve. So this is 2n minus 1 lambda capital D by 2D yn, and what will be yn minus 1? See, wherever you had n, 2, n minus 1 you had no. Instead of n, keep n minus 1 because now your n is different. Lambda d by 2d. All right, now we just have to simplify it over here. If we take lambda d by 2d, this part common from this. Lambda d by 2d is present here also. Lambda d by 2d is present here also. So if you take common lambda capital D by 2d, what are you left with? 2n minus 1 minus 2n plus 3, no? Yes, so this becomes 2n gets cancelled. 3 minus 1 is 2. So 2 lambda capital D by 2d, 2 gets cancelled. Fringe width comes out to be lambda capital D by small d. Now see class, this is the same fringe value for bright fringe also if you calculate. Even if you calculate bright fringe, this will be the exact same value. So you can, and in fact, the derivation from the bright fringe part is easier than this because here you have 2n minus 1. That time you'll be just having n only. So the derivation part is usually not asked from this. You have the usage of this formula only. Note it down. Some few topics, small topics are left. We'll discuss it. Okay, class. Now see, this was the separation between the consecutive fringes. No, now actual angle that is subtended by the central fringe. If you subtend the angle, what some angle also will be subtended because it is thick. So from both the ends, if you extend it, you will get a certain angle at the end. So see, class, that is known as angular fringe width. This is the central maxima. This part is the central maxima. So see, if this is the central maxima, this will be from this end, it will be subtending an angle. From this at the other end also, it will be subtending an angle. So this angle that is subtended at the slit, this is known as the central, angle is known as the angular fringe width. So this is known as the angular fringe width. Fine. So how will you write it? Simply the way we write, no, angle is length of arc divided by radius. So same thing. Length of arc, you'll write it as beta, and radius means here that this separation is this separation. This is the separation between the slit and screen, that we write it as capital D. So this formula also you can use, or you can do one thing. Beta's formula, just now we have calculated lambda capital D by small d. And this capital D cancels, theta becomes lambda by small d. Any of these you can use. One more thing, class. This is when you had everything that we had studied regarding Young's double slit experiment. That was when it was in air or vacuum. Suppose your entire apparatus is kept in a different medium whose refractive index is n. So see, beta in air is what we have studied till now, lambda capital D by small d. If you have a medium that is involved, then this gets divided by n. It decreases n times. So how will you write fringe width in any other medium? You can simply write it as beta in air divided by n. So refractive index is decreasing. Class, this can be asked to you in your conceptual questions. What happens to the refractive index when medium is changed? Oh, sorry, what happens to the fringe width when medium is changed? So it decreases because it will be in the denominator. However, less it will be, but it is in the denominator, so it will decrease anyhow. So we haven't seen any questions from this. Do one thing, note down these 2 points. One question, let us see. So that will perform the work of, that will do the revision also for us, for all the formulas that we have studied, as well as we'll be able to practice the question. See, so this question I was mentioning, this says that, see, there was a figure actually given. I have written the data that was given. Lambda wavelength of the wave is 6,000 angstrom. Separation between both the slits is 10 millimeters. Capital D is 5. Means this separation, this is 10 mm. And if this is the screen, then this is 5 meters. Firstly, we have to find out linear separation of second bright fringe from central maxima. So linear separation from central maxima is yn. Now yn had different formulas for bright and dark. This is given bright fringe. So we'll use the formula for bright fringe. So yn will be equal to n lambda capital D by small d. This was what we had studied, and it is given second bright fringe. So n will be 2. Now put in the values. 2 lambda is 6,000 angstrom. So we'll use 6 into 10 to the power minus 7 meters. Basically 6,000 into 10 to the power minus 10 meters. No, so that is what I've written. D is 5 and 10 millimeters. 10 into 10 to the power minus 3. So this cancels. 5 cancels. 6 into 10 to the power minus 4. Minus 4. Second question. Second question says that same thing for dark fringe. See, same question if you have to find it for dark fringe. Then see yn. The difference will just be in the formula. It will be 2n minus 1 lambda capital D by 2d. This will be the difference that will arise. Right? So here you can put n as 2 when you put n as 2. So 2 into 2 is 4. 4 minus 1, 3. 3 lambda capital D by 2. Put in the data, you'll get the answer. Third part said fringe width. So fringe width was beta. Beta is lambda capital D by small d, independent of the number of fringe. So lambda 6 into 10 to the power minus 7 into 5 by 10 to the power minus 2 also I can write 10 into 10 to the power minus 3. This will be 30 into 10 to the power minus 5, or I can write it as 3 into 10 to the power minus 4 meters. Fine. Last question. Last part. Last part says that angular fringe width. See, angular fringe width, theta. This is lambda by small d we can use. Lambda is 6 into 10 to the power minus 7. Small d is 10 to the power minus 2. This will be 6 into 10 to the power minus 5. Units will be radians. Suppose, let's say there's an additional part which says calculate the fringe width in a medium where refractive index is 2. So how will you calculate? See, in the third part, what you have calculated, this is the fringe width in air. So fringe width in air is 3 into 10 to the power minus 4 from the third part. This is air. So if you have to calculate in a medium, divide fringe width in air by refractive index. So 3 into 10 to the power minus 4 by 2, 1.5 into 10 to the power minus 4 meters. All right. So note down the question, note down the answer. For the second part, those who get their answer, submit. And if you have any doubts in between, let me know.
Ma'am, can I just explain the third part of this question? How did you get the calculation?
Third part, see, you have to here find out fringe width. So fringe width means separation between any two consecutive fringes. Like if it is dark, so first dark and second dark. I hope you know in between first and second dark, there will be a bright fringe. So there will be a complete separation. Let's say here you have one fringe and here you have another fringe. So this one, let's say this is bright, this is bright. So if you want to find out this separation, this is known as the fringe width. This is possible for bright as well, and this is possible for dark as well. So that formula we had calculated, that was lambda capital T by small t. So put in the values, you will get this. All right.
Okay.
This is the answer for the second part, 4.5 into 10 to the power minus 4 meters. Okay, Razan. 4.5 into 10 to the power minus 4 meters. All right, see, this is a small topic, sustained interference. This is just a theory topic. If it comes, you have to write the definition with these conditions. Sustained interference basically means what, class? See, bright and dark fringes, they are present together, but their intensity decreases. I'll show you the intensity distribution curve also. So when their intensities totally do not change with time, all the bright and dark fringes are having a good contrast with each other, means you are clearly able to differentiate between the bright fringes and the dark fringes. That interference, we just specify it by using the term sustained interference. There are 4 conditions. 2 conditions are similar. One is sources should be coherent. Coherent sources we discussed in the last class. What was coherent source? Coherent source. Coherent source we did. Coherent sources means the sources which emit waves that have the same wavelength, same frequency, and a constant phase difference. That is known as a coherent source. So sources have to be coherent, and C class, for interference to occur, sources have to be coherent. Anyways, then you had monochromatic sources should be there, means light from a single source should come. It shouldn't be white light present. When it is white light, I'll tell you interference with the white light separately right now. And slit width means small d should be more, and the separation between slit and screen, that is capital D, should also be more. So sustained interference usually does not come in your exam, but by chance, if it comes, just this definition with these 4 conditions will be enough. Okay, note down this part. Then another small topic like this, if it is a white light, then what will we do? That is left. Written till here.
Last point, ma'am, almost. Done, ma'am.
See, this I was telling you, interference with white light. If suppose you have white light, see the way now we had in dispersion where single light could on passing through a dispersive medium, it could split into all of its 7 colors. So same thing will happen here also. This will spread into its 7 colors. These are all the 7 colors. It's just that it was difficult to depict all of these, but these are all the 7 colors that are coming here, starting in their exact order with your order that is present. And these are also the 7 colors. We call this a spectrum. This entire which you have, we call this one. This entire which you get exactly as the spectrum, this spectrum. So exactly in this order, with your order, the colors get spread, which you call it as this part you call it as the spectrum. Fine. Now see, at the center, you will get a white light. Center, because they'll combine with each other, so you'll get the white light. But now this, as the splits, as they'll be splitting, the fringes that will be formed, these won't be bright or dark fringes the way you obtain. These will be exactly in the order of the wavelength electromagnetics in the electromagnetic spectrum. This will be violet, then indigo, then blue, then green, yellow, orange, red. Same way here also. In this order, exactly in the order of the spectrum. Fine. So, and slowly, these will keep on disappearing. These will overlap with each other, and like this, these will disappear. So, interfere if you use a white light, then this occurs. Quickly note it down. We have to complete intensity distribution curve. Now, intensity distribution curve shows you the variation of intensity with the phase difference. So see, we'll see first for two identical coherent sources. If these are identical coherent sources, then see intensity is written as under root I1 plus under root I2 whole square. So if these are identical, see it's written to identical we are taking. So this can be written as 2 times root I1 whole square, which can be written as 4I. Fine, this becomes 4 times the intensity. And if it is for dark fringes, so formula will be minus, I will be equal to root I1 minus root I2 whole square. So if I1 is equal to I2, then I will be equal to 0 because these will cancel each other. And if these are supposed, let's say, from non-coherent sources, then resultant intensities equation will be used because now we do not know whichever case to take. So I1 plus I2 plus I plus 2 under root I1 I2 cos phi. Now see, we have to see the variation with cos phi. For the bright fringes, it is reaching a very high value, that is 4i. And as soon as dark fringe will come, it will become 0. Then again for bright fringe, it will be 4i, then again 0. Then again 4i, 0 for non-coherent, for coherent sources. And non-coherent sources intensity is independent of the phase difference. I'll show you the graph. See the graph. This part, pink line, this one. See, for all the different values of angle, pi, 2 pi, different phase difference. Maximum for bright, then it is becoming 0 for dark. Maximum again 4i for bright, then 0 for dark. 4i for bright, 0 for dark. And this will keep on moving for coherent sources. Whereas if you plot the graph on non-coherent for intensity versus phase difference, it is independent. So for non-coherent sources, you plot a direct graph because it is variable, not independent. It is actually variable. Independent is for the coherent sources. Here you cannot see any phi. This is variable. This is variable. So depending upon whatever values you have, you will be having different values of non-coherent sources. For usually all the angles, it will be having a similar value because bright and dark fringes concept is lost. One good numerical is there. One more numerical, I have to discuss it with you. Do one thing, class. Note down this intensity part. One more topic I'll do, then I'll start with diffraction. See this question I wanted to discuss. It says that a beam of light consisting of two wavelengths, 800 nanometer and 600 nanometer, is used to obtain interference fringe in YDSE. YDSE means Young's double slit experiment on a screen placed 1.4 meters away. So separation between screen and slit is 1.4. So is 1.4 small d or capital D from our calculations? Separation between the screen and the slit. Yes, Astha.
Capital D.
Capital D. It will be capital D. If two slits are separated by 0.28 millimeter, separation of the slit is given. You have to find out the least distance from central bright fringe where bright fringe of two wavelengths coincide. See, central bright fringe of two wavelengths will be at the center only, but rest of the wavelengths, rest of the fringes that will form will not be coinciding. But it is asking you at one point both are coinciding. You have to find out which fringe is that. First fringe is coinciding with second fringe, third with fourth, anyone. So whichever coincide, their separation from the center will be the same. It means yn will be equal to ym. Let me write down the formula. And since it is given in bright fringes, I will use the formula n lambda 1 capital D by small d. And here let's write m because nn will be confusing. Lambda 2 capital D by small d. Capital D, small d gets cancelled. Now see, n will be equal to lambda 2 is 800 nanometer, lambda 1 is 600 nanometer into m. N becomes 3 by 4 m. Now class, these fringes values cannot be in decimal or in fractions. Like you cannot have 0.89 fringe of first wave is coinciding with 3 by 4th of another fringe. No, fifth will coincide with sixth, third with fourth. Like this you will be having. So see, it means this cannot be this number n or m, both of them cannot be in integration of fraction or any other decimals. So if we take the value of m as 1, n will be 3 by 4. So one of them is coming in fractions. No, this is not possible. M as 2, n will be 3 by 4 into 2. That will be 3 by 2. No, again, this is also not possible. M as 3, n is 3 by 4 into 3. So 9 by 4, not possible. M as 4, as you write down M as 4, n becomes 3 by 4 into 4, which becomes 3. This is the first value which we got. So it means fourth bright fringe of wavelength first will coincide with third fringe of the second wavelength. This is the answer that we were supposed to calculate. So fourth bright fringe of lambda 2 fourth bright fringe of lambda 2 will coincide with third bright of lambda 1. This is the conclusion. Note down this. Once you're done, we'll start with diffraction now.
Ma'am, can you scroll up? Done, ma'am.
C class, understand the meaning of diffraction. Diffraction is basically when the light bends around the corners. For example, you here have a screen. Here is an obstacle. Light will pass straight away from this part. Like this, all the light rays will be straight. But when the light ray will strike this corner, it will bend. All the light rays that will be striking the corner, these will bend while the rest will travel in a straight path. So this bending of light around the corners of obstacle, that is known as diffraction. So wherever you will be having the light part, this will be the light part. So this part which will be deficit of light, this is known as geometrical shadow. So diffraction is the phenomena of bending of light around the corners of small obstacles or apertures and its consequent spreading into the regions of geometrical shadow. Now there are two types of diffraction. One is Fresnel's diffraction, another one is Fraunhofer's diffraction. So in Fresnel diffraction, no, this is the slit, this is the screen, this is the source. All these distances are finite. You can easily count it. In Fraunhofer's diffraction, all these separation are infinite. All these separations, these are infinite. For example, no, we didn't, did we not study the plane wave front like that only? So in your syllabus, you have to pay attention towards Fraunhofer's diffraction that we'll see, that is a diffraction at single slit. So for diffraction to occur, this is the Fraunhofer's diffraction only. Fraunhofer's diffraction. Like this is a source, from the source to converge, no, because we have obstacles, but we want to converge the light rays. What did we do over here? This was a source, from the source light rays emerged and there was a lens kept, so to converge it. So all the rays will converge at this point and these will also converge because lens is kept, no? We have kept another lens so that these rays also converge. When it will converge, here you will get a central maximum. Central bright fringe, which you see, diffraction is very similar to interference, very similar. The physical meaning of the term is different, and physically meaning is also different. Formulas will be different, but many things in the derivation and formula you will see similar to interference. Like central bright fringe was there. Here you have central maximum. Let's say this is some point P, and when the light rays came, let's say this acted as an obstruction. Let's say this screen, this acted as an obstruction. Now see, this is point D. Let's do one thing. Let's drop a normal. This is a normal that I have dropped. This is just for calculation part. This triangle CDN, just for calculation part. Otherwise, this has no use. So C class, if you look at this triangle that is formed, this angle is also theta n, and these are also theta n. Theta n randomly I have taken. Now in this triangle, sine theta will be perpendicular by the base. So perpendicular over here is this. In this entire triangle, this perpendicular is CD. This perpendicular will be DN. This is the perpendicular, and hypotenuse over here will be CD. So in this triangle CDN, if you write sine theta will be DN by CD. So sine theta. Now separation between the slit, that is this value DN. D is this point. This is D point. I hope now it is clear, CDN. And this point was N. This is theta N, that point was N. So here, if you see, DN is the separation between the slits, which I have taken as A. So DN becomes A sine theta N. One more thing, class. In this triangle, let's mark this point as E. Let's say this is some random point E. So if you look at this big triangle, P, let's say this point is O. So POE. From here, if you write tan theta, it will be perpendicular, that is PE. Perpendicular PE divided by EO. Now see, if you remember, separation between slit and screen was capital D. So OE will be capital D only. And separation between the point and central maxima, we used to write it as YN. So same thing. All right. So YN, so tan theta will be YN divided by capital T. So tan theta N will be YN by capital T. So YN will be capital D tan theta N. And if you use small angle approximation, then YN will be capital D into this theta N only. Now I will tell you the conditions for secondary maxima and minima. But before that, note it till here. Secondary minima and maxima are just same things as bright fringe and dark fringe. Note down these introductory points, then I'll tell you the conditions for this. See, the condition for nth secondary maxima, no, that the path difference is n lambda. This minima in diffraction is similar to bright fringes that we study in interference, Young's double slit experiment. Here we have single slit only in diffraction. So path difference for minima is same exactly as what you have studied for bright fringes. So path difference will be n lambda. Now see a sine theta in which we have calculated. This becomes equal to n lambda. And sine theta n becomes equal to n lambda by a. So we use small angle approximation and theta n becomes equal to n lambda by a. This is known as the angular separation. This is known as the angular separation. Now, if we have to find out the linear separation, see, for the calculation of the linear separation, no, that also yn I had written. So yn is equal to theta n into d. So theta n will be n lambda a multiplied by d. This is the linear separation. So C class, pay attention in the exam when it is asking you to calculate the separation. So it can be linear and angular both in diffraction. Same thing if you want to write it for secondary maxima. Just the difference will arise in 2n plus 1 lambda by 2. So theta n will be 2n plus 1 lambda by 2. Here it will be 2n plus 1, not minus 1. Because here you are, because this derivation is not there, so that's why I'm not doing how did you get 2n plus 1. But the angles and the conditions will be 2n plus 1 lambda by 2. All right, class. And for the linear separation, same thing, 2n plus 1 lambda d by 2a. These two formulas, angular separation for the minima, and these two formulas, angular separation for the maxima. Remember this, that is enough for solving questions on diffraction. Noted from here, let's also see some questions then. See, this question says in single slit experiment, light of wavelength 6000 angstrom is used. Slit width, now this time A is given to you and capital D is 2 meters. So you have to find out separation of first, secondary minima from central maxima, both angular and linear. In the first part, you have to find out, see, secondary maxima is given. So secondary maxima's formula. And then you have to secondary minima. So secondary minima's formula is n lambda by A. So angular and linear both. So angular will be n lambda by A. N is 1. So this will be lambda by A only. 6 into 10 to the power minus 7 by 2 millimeters, no? So 2 into 10 to the power minus 3. That makes it 3 into 10 to the power minus 4 radian. And linear, if you have to find out, simply multiply theta and with d instead of writing this entire thing all the time. So 3 into 10 to the power minus 4 multiplied by d, separation between the screen is given as 2. So this is 6 into 10 to the power minus 4 meters. Separation of secondary maxima and second secondary maximum. So see, angular will be 2n plus 1 lambda by 2a. Fine, n is 2. So when you put this becomes 2 into 2 is 4, 4 plus 1, 5 lambda by 2a. Now here you just have to put in the values. This becomes 5 into lambda is 6 into 10 to the power minus 7 by 2 into a is 2 into 10 to the power minus 3. This will be the answer for the angular one. Same thing you have to do, multiply whatever answer you are getting with yn, theta n into capital D. So 5 into 6 into 10 to the power minus 7 by 2 into 10 to the power minus 3 multiplied by 2. Whatever answer you will get for yn, that will be your final answer because D is capital 2, double of it. Intensity distribution, one more thing, class one thing, then you can note it down. This part before we do intensity distribution. See, if you have to calculate now the angle subtended by the central maxima width of it. So it will be simply twice the angle that you obtain, 2 theta n. That will be 2 times theta. Theta was lambda by A. And if you want to find out linear width, it will be angular width multiplied by D. So 2 lambda by A will be the angular width multiplied by D, just in case if you have to find out the linear width. This is the angular width of the linear central maxima. This is angular width of central maxima. All right, and this is the linear width of central maxima. 2 times this y. Fine, note down these this question along with that part, then we'll quickly complete with intensity distribution curve that is left. Now, C class. From here, just note down this part, width of central maximum. Now, see, intensity distribution curve is different in diffraction. See, when you write all the values for minima and maxima, like path difference is n lambda. So for first minima, it will be 1 lambda. For second, it will be 2 lambda, 3 lambda, 4 lambda. Like this, nth lambda, it will keep on moving. And similarly, for maxima, you will get all the odd values. 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, 9 lambda by 2, all the odd values you'll get. So you can see intensity is slowly getting decreased. Here, what will happen? Intensity of central maxima will be the highest. The winner in sustained interference and interference, usually you had a good contrast. Here you have a poor contrast between these. Like intensity is decreasing, I by 21, then I by 61. Like this, it will keep on decreasing. Now, from where did we get this I by 21, I by 61? This is all done experimentally. So you don't also need to go into the details how I by 21, how I by 61 came. But just remember, curve is decreasing, amplitude is decreasing for maximum, minimum, maximum, minimum. Fine. If the question comes, you have to plot this graph. Usually, intensity distribution curve for both interference and diffraction is asked in a single question. So do remember which graph was for which part. Note it down quickly, plot this graph. No need to write the above part. This you already know for minima and maxima. Plot this graph for diffraction. Class, your time is already up. So you all can leave those who have completed. This brings us towards the end of the lesson only. Just a comparison I'll do between diffraction and interference that I'll do. That will just take 2 minutes. Comparison questions because it comes difference between interference and diffraction. All right, that I'll tell you in the next class only. So next weekend we'll start with modern physics, dual nature of radiation and matter, and most probably atoms. These 2 lessons we'll be completing it by the next weekend. Fine, class. Thank you so much. Any doubts you have, let me know.
No, ma'am, no doubts. Ma'am, for the classes that I've missed, how will I get the recorded classes?
Recorded lecture. I'll do one thing, Anushka. Just text me on WhatsApp. I'll share the entire playlist of this batch. So from there, whatever classes have been missed, just tally up with that.
Yes, ma'am.
Yeah. See. Okay, class. Thank you so much. Goodbye.
Thank
Thank
you,
you.
ma'am. Bye, ma'am.
Thank you, ma'am.